Yes, thank you, Phil. So hello everyone. So for those of you who do not know about SAP, let me just give you a brief overview of what we do. So SAP is a enterprise software applications company. We have some popular applications which are in the ERP space, in the customer relationship management, and a host of other application bundle. We recently released the Business Suite S4. So that released last month, I guess, and that was actually a big release for us after maybe 10 years when we had the previous release, the S3. So yeah, we are actually big in the application business application space. We have a lot of customers, around 300,000 plus customers across 190 countries. So and employees spread across the world working for us. My name is Vivek Kandiyanallur, and I work for the database development team. I sit out of the Dublin Bay Area office. So thanks for allowing us to present today on our view of the SAP Internet of Things. So basically, this is our perspective, and we've seen the space for some time now, for the last 10 years or so. And the Internet of Things has always been there, right? So people have always, there have been mobile devices, there have been gateways, and it's been used widely in a very focused way for different segments. But it's really coming of age as of now. So there are a lot of reasons for that. You've heard over the last few talks that hardware is becoming cheaper, more viable. There are better communication protocols. The battery life is, the usage of the battery life is much better, more optimal. So these sensors can run for a very long time. Standards are coming up right now together. And you see a host of these devices being used widely, much more widely than what it's been, right? So it's coming of age. And security is very important. That's one blocking factor. That's one problem why people may not adopt Internet of Things in their business or the environment. So I attended Phil's talk a couple of weeks back on Friday over here. Talked about how the internet grew without thinking about security upfront, right? So the security was an afterthought where we developed things around what we had. So it was kind of messy eventually. But the Internet of Things we cannot delay. We cannot delay for that long, because if you look at it, the threat is out there right now. With the Internet of Things, you actually not only have a problem with your data network or your computer lab or your the actual the data domain which is out there. You actually have a problem with the IoT coming into your homes, your cars, and a host of other places. And they not only deal with data, they also deal with actuators, right, which actually bring in motion. So you don't want to design security as an afterthought after a lot of incidents. You have to think of it upfront and then take it from there. So we saw a lot of this MGC architecture being talked over here. This is similar to the MGC architecture. So if for the M, of course, you have the embedded devices like your Fitbit tracker, right? Then you have the gateway, which is your phone, and C, which is a cloud. So in this, it's a complementary diagram to the MGC architecture where we talk about the edge. The edge can be your sensor devices. It can be it's your gateway, anything which is in the outside of your network, which comprises your lot of devices, your edge processing. All that is over there in the edge network. Then you have the core, which is the cloud again. So the cloud need not necessarily be a public cloud or some web service which resides in your backend. It can also be your in-premise software, right? So that can be your core. It can be a hybrid where you have some in-premise software and then you have some services on the cloud. So that's where the core lies. Then you have the networks, which is the communication network between the actual sensor devices and the gateway, or the network between the actual gateway and the cloud itself. So we actually are pretty strong here in this core area. We have a lot of products run by SAP HANA Platform. We are also getting into the edge. We have a few gateway technologies that we use over there. For networks, we actually rely on a lot of partners to help us out over here. So here are some use cases on how some of our products are used. So for example, you have a streaming device where the sensor actually sends a lot of data at a very fast rate, which needs to be processed in the back end. You need to find out meaningful insights out of that. So but all these devices have different protocols. The way they communicate is different. So you need to have some kind of connector which understands this and translates it into a mechanism, common mechanism that your product can understand. So in this left corner, you see the edge server, ESP edge server. ESP stands for Enterprise Stream Processing. So that's our product, which actually runs queries on a continuous stream of data. And it has some minimal processing that it can do. It can run some filtering, some transformation, and then it sends that transformed or filtered data back to the streaming engine, which is in our cloud, which is the HANA streaming engine, which does a lot more processing and gives you some alerts or actions. You can also persist data in your main HANA core store for doing a lot more business analytics later. You have an industrial use case, and SAP is pretty strong here. Our products are used by a lot of industries out there. So we have our ERP products, and then we have our machine intelligence products. So you can actually combine your information that comes from your sensor devices along with your back-end information that you have from your ERP, from your intelligence, and then you can make sense out of that. So the center one just talks about how the combination is possible using our connectors and using the streaming engine and our HANA database. Then we have one more product called the SQL Anywhere, which is our embedded database. It's a lightweight full RDBMS engine. It is capable of running SQL queries. You can persist data over there. So if you want a little bit more heavyweight processing, if you want to run, let's say, some aggregation or some machine learning algorithms or any computation on the edge where you need to also store data, and you can query using SQL format, you can use this always available product that you have over here. And you have a MobiLink, which is another product which does replication, synchronization from your edge to your HANA engine. So this is different from the actual streaming engine we have, where that is done continuously, but this is done on demand. So you need to define how frequently you want to synchronize what data you have on your edge and your HANA backend. So basically, I'm going to talk about a few of our products which constitute our HANA platform. Then how all this fit together in the overall cloud strategy that we have called the HCP. Some of the solutions that we have built on top of this cloud platform, and some of the what our researchers in SAP are doing in terms of the IoT solutions that we are building, as well as what security challenges that we are facing. Right. So this is the overall block diagram of the SAP HANA database. So we call it as one database. We have one database for a lot of purposes. You have multiple engines. You have a relational engine, which is both your column store and your row store engine. Then for non-relational queries, you have a graph engine and a text engine. So customer applications, they talk to the database not only in SQL. There are some requirements in our ERP space where we also need to run analytical queries, we need to run business intelligence, and they have a different representation from simple SQL. So that's your MDX representation. SQL script is stored procedures. You can write stored procedures, you can write functions. And then you have ways in which you can represent graph models, planning models. So all this are different from a regular SQL database processing engine. So we do have an optimizer which processes SQL and generates plans, and the plans are executed by the execution engine. But we also have a calculation engine which actually builds these calculation models. They are nothing but they are acyclic graphs where you have the actual nodes are the operators and the directed edges are the way the data flows. So we somehow combine all this logic that you have, all these models that you have along with the regular SQL, and we can seamlessly execute it across all these engines. We have standard database features such as logging and recovery, storage management. So one of the selling point that we talk about in HANA is it's an in-memory database, right? It's quite fast. We don't need to persist on disk. We can do it all in memory. And I will talk some of the technologies as to why we call it fast in memory. But we also can, if you want to, persist on disk, right, for your logging and recovery purposes. So here are some of the features that HANA has. So apart from the standard RDBMS features, We also have something called a late materialization. So for example, when you run a query, you don't have to extract all the data out of all the columns, and then you discard some rows out of it downstream. We actually find out upfront what are the rows that match, and only extract columns for those particular rows, and then materialize it later and give the results to the user. So that way you don't have to do a lot of decompression. So one of the things that HANA database has is every column is compressed. We have a host of compression algorithms that we use, which I will talk about in the next few slides. So we don't have to actually decompress all of them to get your results. We have also a row store capability for, and we use it for storing our system catalog information. There is a lot of parallelization involved at multiple levels, across columns, across rows, across partitions. We try to avoid indexes as much as possible. So one thing about indexes is you have indexes, it makes your lookups faster, but then you also have to maintain them, right? For every update, for every insert, you need to actually add to your index data structure. It doesn't work very well for ad hoc queries. You'll need to, for sometimes you may have to, for your workload changes, you'll have to redesign it. So we try to avoid it, and we say that even without indexes, we can perform pretty well, because we do a lot of things which I will talk about in the next few slides, such as optimal compression. We work closely with the hardware. We use our in-memory processing, where we do a lot of vector processing. So we actually compute on the fly. We don't need to actually traverse indexes to find your data. There are a few exceptions, of course, and then you can create indexes if you want. We give you the capability, but then we try to avoid it. And the default store for our HANA database is a column store. When you say create table, it's created in a column format, but if you want, you can create it in a row format also. So this is just a representation of the row format and the column format. So in a row format, you have contiguous values of a row stored next to each other, and then one row points to the next row and so on. In a column, you have all the values of a column stored contiguously in memory, and the columns actually point to each other. So in this example which I said, right, I talked about late materialization. So if you want to find out the sale of your corn product, the aggregation of that group by country, you don't have to extract the product column. All you have to do is you need to find out all the row IDs that correspond to your product column, and similarly you can find out the row IDs that correspond to each country. You can use a bitmap AND operation to find out the common set of row IDs, and then you can only decompress your sales column and find out the corresponding row IDs that you want for each country, and then run the aggregation on that. So it's a little bit more optimal than what you would do if you use a row database, where you extract all the data, you need to split it up, you need to combine it again, and then give the output. So I mentioned that you have compression, right? So every column is compressed and stored. So we use one thing called, we actually compress the column data using a dictionary, and this is used for all columns in the HANA column store. So an example here is, if you have all the values of your column on the left side, we represent that in a vector, and the corresponding index of that vector is your value ID, and we store that value ID in the column array, the column vector array in memory. So you actually end up saving a lot of space over there, and the dictionary is also sorted. So that's one reason why we say we don't need indexes. You can actually do a binary search, and it's pretty fast to find out which value you're looking for, right? So, and one more thing we do is that so we do not actually work on fixed 32-bit boundaries. We actually, for example, let's say you have 64 unique values in your column, right? To represent those 64 unique values, you just need 6 bits. So all we do is we just use 6 bits to represent each value in your column, and all those 6 bits, for example, in a 32-bit word, you can store 5 such values, right? So we cross word boundaries. We don't actually use one word for one value. So that way you compress it even further. And since all these are sorted, if you look at it, if you run a range query, right, where you want all values less than, let's say, Miller, since it's already sorted, you can find out all the values that correspond to that query which is less than Miller, and then find out that value IDs and scan value IDs and find out what rows you're looking for. So this dictionary compression. Apart from dictionary compression, you also have a host of other compression technologies we use. So once your actual value IDs are stored in your column vector, you can further compress them using a host of other compression technologies like run length encoding, where it's useful if you have multiple repetitions of values. You can use prefix encoding and so on. So we also reorder some of our value IDs in the column array so that one of these compression technology fits in. We have to be really careful there because we can't reorder all the column vectors in a table, because one row ID must correspond to a particular row position in your column vector. So you only have to compress, reorder maybe one hot column, and then that can be in turn run length encoded or whatever encoding works well for it. And in the HANA Store we have two storage layers. We have what is called the Delta Store and you have the main store. So one thing we did before we designed all of this was you have these typical benchmarks, right? You have this OLTP benchmarks, which is TPCC, you have OLAP benchmarks, which is TPCH, and you find out what kind of queries run generally on a database, right? So usually it is mostly read only queries, and there are very few update queries, write queries. And to add to that, we also did a similar benchmark on all our ERP applications that we have at SAP, and we found out that it is mostly read and very less write, even lesser than TPCH. So to optimize our applications, we had to write a database which is more read optimized, right? So that's where the main store comes in. So in main store, the data is very highly compressed, like how I showed you earlier. The dictionary is actually sorted, and then you have heuristic algorithms to find out secondary compression, which was the reordering of the value IDs I talked about, and it works pretty well. But then of course you do have the reality of updates, right? You have updates, you have inserts, you also have to handle that. And for every insert, for every point update, you cannot go about resorting the dictionary. So we have what is called the Delta Store. So all your inserts and updates go into your Delta Store, and you have a dictionary over there also, but we don't sort it. It's only an append only dictionary, and we use MVCC, so we don't have to we just mark the rows which are deleted. So your update is a delete followed by an insert, right? So when you do an update, you tell your MVCC that this particular row ID is actually should not be visible to transactions that start later, and your whatever data that you inserted should be visible from now on. So that's what the Delta does. It's an append only optimized store. It's unsorted, and but the problem now is if you want to run queries, it has to look at both your Delta and your main, and it needs to join the data and run some processing. Yeah.
I would assume that compression would slow down because now I have to spend CPU cycles to do less. The concern is whether I spilled the disk.
Yeah.
This is all in memory. I would understand use compression so that you can fit more on your memory database.
Yes.
I don't quite understand what are the trade-offs such that compression actually lets things run faster, just because you're thrashing less of the cache, or?
Yes, that's one thing.
Just sort of more generally,
Sure.
This approach, this looks like a log-structured database, right?
Sure.
And the systems to me, log-structured systems are designed for write workloads.
Yes.
That's where the read set is much smaller than the overall set. So it's fit, which means you read in memory, and then writes are optimized by using the log.
Yeah. So the thing is, yeah, one thing is once you compress the data, you have you can run operations on a lot more data in one go. For every CPU instruction, you can use a lot more data on it. Secondly, you don't have to decompress to actually run your queries. You can actually run it on the compressed data itself. So that's one big advantage that you have. So those are the two things that I can think of right away as to why it is much better.
Yeah, so my take was under the assumption that you decompress the data.
Yeah.
The operations on it.
Yeah. So that's where the late materialization comes in. Yes. Any other questions? Okay. So yeah. So we have the Delta Store, which I said was append only, and it keeps growing and growing, and then your queries have to touch both the append only Delta Store as well as the main store. So we do something called a merge, where we merge all the data time to time periodically. either you can set the merge interval, or the resource manager figures out that okay, it's time to merge right now, and then merges the data from the Delta store onto the main store. And when that merge happens, it resorts all the data and puts it in the dictionary over there. So then once again your read queries are much more optimal than what was before. We do a lot of parallelization. So this is just one example where a single core runs on all the values of a particular column, and another core runs on another column. We also do, you can parallelize based on your partitions. You can vertically partition your data, you can horizontally partition it, and each partition can be assigned to a core. Even if you do not partition it, we can actually, by default, when you run your query on a particular column, we automatically partition it based on what row segments need to be processed, and you run your queries on them, and then they are joined later. So we do explicit as well as implicit parallelization on your data. And it works across a lot of levels. Every user may have a different thread, may work on a different core. Your operators in your query tree can be parallelized depending on what scans need to happen on which column. And then of course all these partitions that you have over here. We use we collaborate with the hardware vendors, and we do a lot of their vector processing. So some of them have their SIMD chips, and we make use of that extensively. We take advantage of the multi-threading and so on. So we collaborate very closely with the hardware vendors in optimizing our data processing. So this is the overall picture of all that I talked about. There are a few more things that we do. We do cache locality, we do a lot of such things which I have not spoken about here, but to give you a general idea of what our database does and the top modules, this is just the final diagram. It shows you the same things which I talked about earlier. You have a row store, column store, a graph store. You also have a GIS store, which is your spatial engine, which can run simple random text queries, normal search across all your data, which doesn't necessarily need to know about what columns are there, what tables are there. You can just run a random search query. So basically we support structured data in the form of relational data in your row store, column store, unstructured data in the form of your spatial data, semi-structured in the form of your graph data. And then we also have a lot of other extensions that you have to the HANA platform, which include federation, which means that the HANA platform can talk to other databases. It can talk to Hadoop. So it can intelligently split your queries into parts which need to be executed on Hadoop, bring them back here, join them, and give the results back to you. It has streaming engines, which we saw briefly. Yeah, so these are all extensions to our HANA database, and all this form our HANA core platform, on which all our applications actually talk to and run. So any questions you have here? Yes.
Is that going to cause a major redesign for HANA, or how is it going to interact with like large data volumes?
Sure.
The responsibility of the stream to filter, or HANA?
Sure. The question is, so basically we have our HANA platform, and then I also talked about a streaming engine. Do we need to redesign the HANA platform to actually interface with the streaming products that we have, and do we lose out on performance as a result, right? So basically the streaming products that we have are on the edge, or they actually talk to HANA using our internal protocols. So we don't have it inside the HANA engine, but we have it in a HANA platform. So we don't have to redesign our core engine, our column store engine, or a row engine, and all the filtering happens in our streaming engine itself.
Does the user pick to control, so if the user writes the application, do they have to explicitly say this is the piece that I want as a filter in the streaming?
Yes, we give controls to the end user to find to what data model, what schema they want according to their needs, and they design. We have actually a streaming language, which I'll talk about more, which looks like SQL, and you can actually write queries that you want on your window to constantly process, and what kind of filters that you want. And HANA actually has adapters which subscribes to the output of the streaming engine, and that is ingested into HANA. So the streaming product can be used as some kind of first level filter where when data comes at a really fast rate, you want to just throw away data you don't want and just put in minimal data that you want HANA to process, or historical data that you want to
So
join.
intuition, how much can you find?
It depends actually. If you have really good hardware and you don't care, it's you don't need that big of a filtering. It depends on your use case. So there are some TPCC, I'm not sure if we have our own sales and distribution benchmarks which are published for our applications. So I guess there are some numbers over there publicly available. If you search for S&D HANA, you can actually find out some really good numbers. I don't remember the top of my head as to exactly what numbers they are.
Just to follow up, imagine if I have a kilobyte of data, I don't need HANA, right?
Yes.
But so imagine there's some sweet spot or some range, or large range from which
Yes.
you sort of expect HANA. This is the sort of scale of data over which
Yes.
is really well suited.
Yeah.
Give it some sort of rough intuition as to what that range is.
Yeah, so our HANA platform comprises of multiple products, right? We have an embedded database where that kilobyte kind of data works pretty well. It's not that expensive, and then if your HANA product, you can actually, there are options. You don't have to get the whole thing. You can actually license select components and build your HANA database at. If you really want really big data processing, then HANA makes a lot of sense. Or if you want regular processing for your applications, also HANA makes sense because we are not only a platform, we also provide you a host of applications. So you can have end-to-end solutions for your problems and not just design the solutions on top of the platform itself. And our applications that we have, our ERP applications, they run best on HANA as opposed to, let's say, Oracle, or they're tuned pretty well to HANA right now. So it gives you really good performance if you use the entire ERP along with the HANA database as of now. We also have other databases. We have databases from the Sybase acquisition, which is the ASC, IQ, which are more disk-oriented databases, and they have a better TCO. So if you want that, there was a part of your HANA platform. You don't have to get a full in-memory HANA engine if you don't want it. So it's actually depending on your need, I guess. So yeah, so let's talk about streaming, which I think there are a lot of questions over here, and let's look at its how it works. So yeah, so basically it's an event-driven engine. So you have a bunch of events, which could be your market algorithmic data, which comes in your stock feed. It could be sensor data for the IoT case. It could be your web clicks, or whatever data that comes in has to be understood by the streaming engine first. So first you have an adapter which translates it into a particular format, ingests it, and all these streams have, you need to actually run some analytics on top of it to find out what they mean, right? So that is actually performed over here. You can do basic filtering. You can throw away things that you don't want. You can transform it into a different output stream by joining it with other streams. You can actually combine the data with your application data to have a little bit more logic, but there is nothing persistently stored here. It's all done in memory. We do have the option where you can overflow data onto files, but you don't have a RDBMS or a database engine which actually at the edge where the stream, the event processing server resides to actually store the data in a DBMS format. So once that is done, you actually output it into your dashboards, your message queues, or applications, right? So it's event based. So you need to subscribe to an event, and it gets transformed. And you need to subscribe to the output, and you need to specify the window. Yeah. Sure. Yeah, you can actually find out what the tables are which correspond to a particular stream. That's the maybe you can say a simple example is, for example, you have in an industry you have a machine, and you want to find out the maintenance schedule on that machine, or you want to find out the warranty on it, and then you have sensor data coming from the machine saying if the machine, what the machine temperature is, how is it functioning, and you want to kind of perform some logic whether it's functioning okay, and is it in warranty, or when was the last maintenance performed. So things like that, right? On the edge, you can actually directly process that.
This is an impossible to answer question, really, but I'll still ask it. How difficult is it for people to use this? Is this a widely used feature that people are able to bring in this historical data, or is it difficult for them because it seems like there's someone in their head that has this mental model of the performance of the event processing system, all the quality that's going on with the filtering and everything, and they have to execute this SQL query to bring in the relevant data. How do they make that decision?
Yeah, so it's basically the modeler that works for the enterprise decides what kind of streams I need to have and what those streams mean in terms of the backend data that is stored, and then they actually create the schema in the backend, and then they create the continuous queries that need to run and the windows that need to run. So yeah, you do need to have the big picture as to exactly the actual logic as to how to combine them, how to split them. So that level of expertise you need to know. You need to be aware of your data flow over here. One more thing that can be done is you can use it as a simple filtering service. You don't have to do all this joining. You can actually, the output stream can go into your HANA database, and your HANA database DBA admin can actually figure out what to do and then trigger events from there. It doesn't have to come from here. You can either push your processing to the edge or you can push it to the cloud, the backend. Right now we actually, yeah, second one is more common. This the edge processing thing is something actually we are working on right now. So it's not only about we also have to take care of the computation power that you have on the edge. We don't have too much of it, so it's more of a lightweight engine compared to the similar ESP engine which sits on the cloud on your core side. So this one example that you have here. So this for a stock. If you want to find out the book value of your portfolio, your investment portfolio, right? So you have the stock feed that comes in of various positions that you have in your portfolio, and then you also have what all positions that you have. You can run, let's say, a volume weighted average price on your price feed, and according to whatever positions that you have. For example, your stock, for your yeah, so various positions that you have in your portfolio, you can actually find out what that weighted volume average price is, and you can actually combine that, aggregate that, and find out what your overall portfolio value turns out to be. So this is just one use case where the ESP can be used. So yeah, there are two parts. One is the actual capturing the data, and one is the continuous queries that you keep constantly running on it. So the capturing the data, you can do it using simple micro batching principles, where micro batch is a small batch, right? So you can define the window where you want to continuously run your queries. You can actually filter it, you can join it with other streams, like I said. You can also give some more value to your streams, right? You can, based on your data that you have stored, you can prioritize it as to which is more important, which has to be processed right away. At the analysis side, you need to detect patterns on that, and then you need to, once you do that, you can actually generate alerts to find out what went wrong. So one difference between a simple, let's say, event processing, simple event processing engine as opposed to this is that you need to find out correlations between different streams. A single stream may not make sense sometimes. For example, that engine data that I said, the example of the machine that I said, where a machine may, there might be a sensor on the machine which talks about the temperature on it, and if it exceeds a particular temperature, it means something is wrong, it's overheating, right? So, but if the temperature outside in your workshop also is pretty high, it doesn't mean anything. So if you have your workshop temperature reading in the yellow and you have the machine reading in the blue, you can kind of correlate that the workshop temperature is just 30, the machine temperature is 90, so there is definitely something wrong. I need to do something, I need to take some action. So that correlation is possible in this kind of complex event processing engine that we have. So this is at it's called the continuous computation language. That yeah. Oh, God. Yeah. Okay. So this is the it looks similar to SQL, right? That you can actually create tabular kind of schemas. You can actually filter it. You can join it, and so on. And this is what we were working on that I mentioned earlier. It's a lightweight engine for doing it on the edge. And SAP is actually really it wants standardization in terms of the communication channels that it has. So it's working on adapters, it's looking at the industry, it's trying to contribute into standardization. There are RESTful APIs actually to talk to the backend cloud. So I think I'm way behind. So SQL Anywhere is our other product. It is an embedded database. It can store data persistently. It actually runs on ARM processors. MobiLink is our synchronization technology, as opposed to the ESP, where you actually have a constant stream. You need to explicitly say what you want here. It can actually, you can scale it also across multiple SQL Anywhere gateways that you have, talking to different sensors. You have a load balancer in between, and you have multiple MobiLinks which you can set to talk to which SQL Anywhere you have, and that in turn talks via ODBC to your backend HANA database. So yeah, so SQL Anywhere is actually a complementary solution that you provide to your actual core engine and to your ESP product that you have. So it's durable, bidirectional, and yeah. So apart from SQL, one thing about SQL Anywhere is that it's lightweight, right? It's less than 20 MB, right? So it can sit on a Raspberry Pi. We also have something called ultra light database, which is even smaller than 20 MB, and that is a really small embedded database, and that doesn't have all the database operations like views and all that are not there. So if you want that product, we have that. And everything, all of that I talked about fits into this IoT Cloud Platform offering that we talked about. So you have this, on the edge you have our various products there, you have our application sitting over here, and you have a cloud platform with the database sitting right in the center, and you have dynamic tiering. If you don't want all your data in memory, your cold data, warm data, we can use dynamic tiering to actually store it on our disk-based databases that we have. You can talk to Hadoop, you can do smart streaming. So that forms our core HANA platform, which I talked about in the first part of the presentation, and you have this IoT applications which can be built on top of that using this architecture. So these are some of the IoT solutions we have today. So we are strong in the industry IoT, industry Internet of Things. We have been doing a lot of things in the manufacturing space. We also are expanding to we have products in the connected, the retail, the logistics, and the retail space. So we intend to provide solutions using our HANA platform stack on various segments of the industry. So predictive maintenance is one thing that we have done quite a bit in. So it's nothing but finding out if a product is about to fail very much in advance. If you find it out too late, the cost is too high to replace it. You may lose out on your assembly line, your supply chain. So we need to, based on whatever early signals that come in, based on your temperature readings, based on how much your engine knocks, the vibrations that happen. So our predictive maintenance solution actually detects that early and informs you when it's going to fail. So this is the architecture for that. So it's pretty much similar to some of the slides that I showed earlier, where you have the machine data which comes in, you create a data model. We have a prediction engine here which uses that model to find out if there is any anomaly in your data, and then it, for example, it says that sends a message to the sales representative to order a new machine, or it tells it's still in warranty. I need to call up warranty to find out what can be done for that, or a service engineer alert is sent to the service engineer to come and fix it, right? So all this is automated, and this is the entire flow of that, right? So you connect it, you find out, you monitor it, and you schedule a work order to fix it. So it's end to end, right? This is one more example of some of our innovative solutions. So we have collaborated with the University of Guelph to create a smart green roof. It's nothing but on top of buildings you can actually have some plants or some crops growing out there. It's actually pretty useful because your building's temperature is kind of controlled. In the summer it's not too hot, winter it's not too cold. It also I mean, you can also use it for rainwater harvesting, so that water doesn't flow off the buildings. It can be collected and stored over there. So it has a host of benefits. So the agriculture part of it, the technology came from University of Guelph, which is in Canada, and we are actually providing our products to actually figure out how to automatically maintain it without somebody having to go every day and figure out how to water it, how to keep it alive, and things like that. So these sensors find out what the humidity is, what is the actual temperature on the crops, and we have the SQL Anywhere database sitting on the edge itself, which based on whatever information comes in, it runs some actuators where it turns on the irrigation channel and waters the crops. So things like that are possible here. This is the last few slides, I guess. I'm almost done. So with respect to the IoT, we see that the sensor devices are very restricted. We cannot do everything that a regular application does, right? They have a lot of limitation in resources. You need to manage your power better. You cannot use traditional security mechanisms. You can't have a full-blown publicly key encryption, PKI, on your edge device. You cannot have full support for XML. The devices are unreliable. You cannot patch them often. You cannot. You don't have a dedicated DBA to fix it. There are so much diversity in devices and communication protocols and so on, right? So those are some of the problems we see, and these are some of the past projects our research teams have worked on. So context-aware security policies is just a simple example. You're a patient. You're sending your patient data to your doctor all the time. For example, there's an emergency where your data suddenly shows a spike in some reading. The doctors around you or your nurses just around you need to be able to see the data to take some action on you, right? They need not see it all the time. So based on the context, it's not just the ID, what authorization you need to have. It also depends on where you are. So one of our teams actually extended the XACML standards for supporting that. Secure handshake is another protocol where an example is you have this multiple barrels of highly reactive chemicals which are being transported, and one barrel of certain chemical should not be kept to another barrel which can react with it, right? So but each barrel cannot just openly say that I'm here to anybody, because that person you don't want to expose that we have a reactive chemical right here. So somehow it needs to figure out that the barrel next to it is something that is reactive with this, and there is a danger. The shop floor manager, the storage manager needs to figure that out and take some action. So that was something which a protocol which one of our teams worked on. There is trust of sensor data. There is privacy preserving, where as the in your supply chain, as your product flows through different segments along with your different partners, you need to actually each partner or each segment should not know the entire direction. The end manager should know all the things that have been done to the product. So some privacy things done over there. The current project that we have right now is the predictive analytics of pipelines. So a big city actually has a huge water pipeline network, and they want us to run predictive maintenance on it using smart sensor data that they provide us. So they provide us the actual water debit information, how much water has actually debited, and it also provides us the pressure on the smart meters across the water distribution network. But they don't want us to reveal us the actual information of where that meter resides and whom it belongs to, and also the actual water distribution companies. It wants us to anonymize the data. So we need your help in some of this. So that's one reason we are affiliating with you. So we have a bunch of researchers already researching on this, and we would love to collaborate with you on this. We also want to figure out what kind of end-to-end security we want to do. Do you want to run homomorphic encryption? You want to do order preserving encryption on your device itself, but the device doesn't have a lot of power. What kind of how do you do key management on the device, right? So things like that. So we have some basic solutions, but they're not really. You can't say they would pass a security researcher that this is industrial strong solution that you have right now. So this one area we see collaboration, scope for collaboration with you. Another area is in our core itself. So we have done some work in privacy preserving in the cloud, in reputation systems. Searching over encrypted data, we have already talked to one of your researchers, Raluca, who created the CryptDB database. So we have actually taken that CryptDB and implemented it on HANA. And some of the limitations of CryptDB we have overcome in terms of, in CryptDB you cannot actually do ordering on aggregate data. So we have solved that problem. So right now every possible query can actually run using seed, but performance is a problem still, right? So we are having a lot of problems with aggregation, performance on aggregation. So that's one area we would like to also work more with you. So these are the actual numbers. So you can see that the aggregation numbers are actually pretty high, but search joins are all pretty good over here. So the challenges that we see in this project is, as I said, the aggregation performance of aggregation queries. So if you are aware of the CryptDB protocol, there are onions of encryption that are performed on each column, right? So we would like to reduce the lower encryption onions that are performed. to actually run our queries. We want to make it more secure. We want to reduce the time it takes to encrypt the database. Suppose your keys are stolen, we want to re-encrypt the whole database. How do we do that? It doesn't make sense of sending the data back to the client, him re-encrypting it and then sending it back to the server, right? So these are some research problems that we are working on right now. So these are some of the collaborations that we have done in the past, and all these are the universities we have worked with. This is actually a very limited number that we have. It's only for the SAP HANA platform. Your applications team also has collaborated with a host of different universities. So yeah, so that's all I have, and you can, yeah. I went really fast in the end, so sorry.
You mentioned earlier when we were talking about green roofing that you were working on self-maintenance or self-maintenance.
Yes. Yes. So for example, you have these plants on your roof and they need to be watered, right?
No, I know what it means, but can you explain them specifically anything you guys do?
Yeah. So specifically, we have some sensors which actually send out moisture information, which includes the substrate moisture information and the moisture outside in the environment outside. So that information, once it comes to your SQL anywhere, it can actually find out based on that and the ambient temperature outside whether you need to trigger irrigation pipe and turn on the water supply and water it. So that's just one example as to based on what reading you have, you water the plants, right? Yep.
Isn't this SQL Lite works? It's able to work with a Raspberry Pi.
Yes.
So is there an ability for, let's say, a student or someone who's interested in working with IoT to get the HANA platform like a light version or
Sure.
small to
Sure.
put some smart things in their house using, let's say, Raspberry Pi or an Arduino
Sure.
control?
Yeah, so I think right now we have developer editions of the products which can be downloaded. Apart from that, once you start collaborating with us, of course, all these products are there for use to find out what can be done with them. Yeah, sure. You can send me a mail or you can tweet me. And this Anil is our chief architect. You can also talk to him about it, and you can we can figure out how to collaborate and work on this, take it forward.
I was struck by most of the IoT applications seem to have a long time, relatively speaking, from data collection to implementing actions. Even in the predictive maintenance, it seemed like it was on the time scale of like minutes or hours, where you could imagine like a centralized solution working. So you don't need to push the predictive piece, if you like, anywhere but in a central piece to serve those applications. But going forward, do you see other applications where that time window is shrinking, or is this kind of the sweet spot for everything that
Yeah, we do. There are a lot of applications where we need to take action right away. For example, the health application I talked about, we cannot wait as long as going to the back end and calling the doctor who is supposed to come and take care of the patient and fix whatever problem there is. The nurses who are actually around the vicinity, they can actually, whatever, right, information that comes from the patient sensor readings can take action and go right away. The window is a little bit more smaller than, let's say, on an industrial strength where the actual machine needs to be replaced. Outside of health, I'm sure there are. So for example, right, you have an oil rig. The oil rig is totally disconnected sometimes, right, from your, it's offshore, it's located somewhere in the edge. And you need to kind of fix how much to drill and how much to, if your machine is about to stop working, you need to kind of say drill less or stop this valve. Things like that intelligently have to be done automatically in the edge itself, rather than it come to your main processing data center where it's some queries are run and then information is sent back there to stop that. So some kind of intelligence need to also stay there.
You're a preventative maintenance sort of by definition, you have a long time window, but think like the check engine light on your car. That's an event where like, no, you want to deal with this right now. Or out of oil, the out of oil light on your car. Out of gas will do it. Yeah. Well, that will be dealt with normally. Great, thank you so much.
Yeah, thank you.